Hey everyone, welcome back to my YouTube channel Build AI with Sandeep. In the last two videos, we talked about generative AI and large language models. If you have not seen those videos, then please do watch out those videos so that you can understand this video. Today we are going to discuss about the transformer architecture. So as you can see on my screen, there are various components inside the transformer architectures, and before moving into the today's video, I'm going to give you some context about the transformer architecture. So basically, as we all know, large language models are nothing but predicting next token. Okay, so this transformer architecture help LLMs to predict next to generate next token. So as you can see, this transformer architecture is very complex, and uh, basically there are various components. So what we can do is we can understand each and every component of transformer first, and then we can cover up the transformer architecture, the whole working of transformer architecture in the next few videos. Okay, so this architecture introduced in 2017. Why? Because previously there was no architecture available that we can train text data on that, and that this transformer architecture has very special things, few things that are really important, that are very special inside by in using this architecture. So first of all, if anyone ask you this question that in which year the transformer architecture came, in 2017. Okay, now in this video, let's quickly write down what are the key important things we are going to discuss. I'm not going to discuss this architecture, the whole architecture working. I will just discuss the few important things that you need to know before understanding this architecture. And trust me, everyone, that this is really very important thing to understand. This is very important thing to understand if you want to make your career, in the field of AI. So everything starts with this architecture. So so let's first understand why part of this. Why this architecture came? Because previously there was no architecture that can do parallel processing of text data. Parallel processing of text data. The second thing is we could not use full use of GPU TPU. There was no model available that can leverage the full power of GPU and TPUs. And the next one is there was no model available that can handle long text sequence, long text sequence. So to solve these three problems, this architecture came. And previously there was models like RNN and LSTM that can be trained on text data, but these three problems was there in the two models, RNN and LSTM. Okay, so in 2017 this architecture came, and we can do parallel processing. We can pass full sentence to this architecture as an input, and it can process and gives us better context aware embeddings. Okay, So let's understand, let's assume that we don't know anything about this architecture. We don't know. We just know that LLMs can generate next token. That's it. Okay. So let's one by one understand each and everything so that we have some kind of understanding how LLM can generate next token. And I'm saying that using this architecture, LLM can generate next token. Okay, so in the encoder part, what you guys can see, let me copy this image so that in the, or we can do this thing. Okay, so I hope you can see the image. So we are going to discuss only this part today, only the encoder part of this architecture. So we all know that what is encoder. The the left side part is basically an encoder. This is, so this left part is basically encoder. Okay, and what you can see in the encoder part, let me copy and paste it into the next page so that you all can see better. Yes. Yes. Now I guess you all can easily see what are the components available in the encoder block. Okay. So there is, so we will go from bottom to top. We will go bottom to top. Okay. In this way. And the very first thing in the encoder part I can see is input. The second thing I can see, positional encoding. Positional encoding. The third thing, what we can see, multi-head attention. This is the main hero of the whole story. Fourth thing is add and node. The fifth thing is feed forward neural network. Okay, so these five things we are going to discuss in this video. So first of all, uh, the very first thing I want you to everyone know that machine cannot understand the text data, and using this architecture we are only working with the text data. Okay, so let's suppose we have a large amount of text data. For now, to understand the first part, so for to understand the input part, what is the input of for this architecture? I'm saying that machines cannot understand the words. So we need to have some kind of terminology that can convert words into the vectors, because vectors can be easily understood by the machines. Okay, so let's take an example. We have cat drinks milk. Okay, we have to make you everyone comfortable with the concept, how we can convert words into the text. So I'm saying let's take an example. So first what we can do is, we have a sentence having three words, then we can convert these words into unique IDs. We can assign unique IDs. Okay, so let's assign 101, 92, 104, 103. Okay, so we assign cat a unique ID. Then the next thing what we can do is, we can assign cat a random vector, point 0.2, point 0.3, whatever be the size of the vector, we can assign a random vector. Similarly, we can assign a random vector to the word drink. This is also, but with the same length as cat. Okay. Okay. So now I'm saying that we need to assign a unique ID to each word, and then after that we need to assign a random vector to each word, so that machine can understand and process that vector. Okay, and the whole process is known as tokenization. Tokenization. So, in training of these large language models, what we can do is we can create a vocabulary. We can create a vocabulary, uh, vocabulary of unique word. Vocabulary of unique words. Okay, so let's suppose we have 1000 unique word. Okay, so we are creating a vocabulary, and in fact we are creating a dictionary. In Python, you all can be aware about the dictionaries. What are dictionaries in Python? So what we can do is we can assign, we can take unique word, all the unique word in our text data. For example, a Sandeep. The next word is, okay, so a, yes, yes. So A is coming on first index, Sandeep is coming on second index, then we can say M coming on third index, then we can say AI is coming on fourth index, so and so on. Okay, so we are creating the vocabulary of all the unique words and assigning index to each word so that we can get the unique ID of each token. That is what we did in this example, that cat drinks milk. So just imagine this is our vocabulary and cat is coming on 101 index. So we said 101 is the unique ID of cat. Okay, now after that we do vectorization of each unique ID. We assign a vector to each unique ID, and the vector is random. Okay, random. Why we took random vector? Because after that we are training neural networks. We are using fully connected layers, and there are weights and biases, learnable parameters to adjust this random vector. So when the training completes, these random vectors are will be changed according to the context and meaning of the word. Okay, so when we when we get the vectors of each word, the then we have then we reach to this point. And what is the point? Input embeddings. Okay, so embedding, what do we mean by embeddings? So let me write just one. So input embeddings. So embeddings is a mathematical representation representation of words so that machines can understand easily. Okay, okay. So embeddings are mathematical representation of words so that machine can understand easily. And embeddings are nothing but a dense vector. Embeddings are these are a dense vector. Dense vector. Okay. So now we reach at the input embeddings. So you all now have an idea that what are input embeddings. These are vectors that represent each word. Okay, okay. Now let's move ahead. Then we have positional embeddings. Positional embeddings. Why this in transformer architecture? Why this? Okay, let let me let me paste this image, and I'm pasting it right here. Okay, maybe something is wrong. Let me again try. Okay. Now we are looking at this one, this thing, positional encoding. Why this positional encoding? We are we are adding this positional vector to our input and embedding so that our model can have the information of the position of the words. Since embedding, since for example, cat drink milk. Okay, this is our sentence initial. This is our input basically for the for our model. So we created a dense vector for cat word, similarly for drink word, similarly for milk word. Okay, and let's assume that dimension of each word dimension of each word is 3. Okay, so we have a list of 3 vectors having dimensions of 3. Okay, now our model does not have any information about the positions. So what we can do is we can create a new position vector and add up to our initial embeddings, input embeddings. Okay, these are our input embeddings. Now positional embeddings. Now you all might be thinking that how do we create positional embedding? Positional embedding is nothing but it is also a similar list of 3 vectors having dimension of 3. Okay, but what is data inside these 3 vectors? Okay, now for example, cat is coming on 0th position, drink is coming on 1st position, and milk is coming on 2nd position, 2nd index. Okay, so now in 2017 research paper, there is a formula to get these 3 vectors. Okay, so so as we all know, as we all know, uh, there might be even index or odd index. Okay, we all know. So there is a formula that is mentioned inside the research paper, position to I for even index. For even index. Okay, using this formula, sine of position 10,000 2i divided by d. Okay, and for positional embedding for 2i plus 1 odd index equal to cos position of 10,000 2i by d. Here, what is pos is equal to token position that we have 0 1 2. Okay, and d is embedding in embedding size that we have 3 in our case. I is dimension index. Okay, so using this formula, we can create positional embedding that can give us the list of 3 vectors having size 3. Okay, and now let's let's understand why the sine and cosine to compute the positional embeddings, because sine and cosine graph is smooth. Since we know sine is graph is something like this is smooth, and cosine graph is also similar like this. Okay, and the reason why sine and cosine, first one is smooth curve, and the second reason is they repeat they repeat they repeat after a certain interval. so that model have the information about the length between the words, so by adding the positional vector to our input embeddings, we are giving information about the position of the words to our model. Okay, so now let's move ahead. Now let's discuss about the what is this multi-head attention. Multi-head attention. So this is the main hero of the story. Now we understand about we discussed about positional embeddings. Now first let's understand what is self-attention. What is self-attention? What is self-attention? So previously we did not have any mechanism that can extract context from the sentence, from the word. Okay, so let me give you an example first, and after that you all can understand easily. Suppose I'm saying apple. Okay, okay, apple, and apple have two meaning. What are the two meaning? Apple is a company. Apple is a company. Also apple is a fruit. But our model, how do our model understand what apple refers? Okay, how? So the one way, the only way to understand what apple refers in a sentence is that by looking at other words in a sentence. For example, I am using Apple phone. Okay, and the example one, and the other example is I am eating apple. So apple word is same, but the two sentences are different. Okay. So by looking at other words, for example, in first sentence, phone. Phone is referring to Apple company. Okay. And using is Apple. It is a phone that I'm using. But in the second sentence, apple, I'm eating apple. Okay, so this word have different meanings, different context. This word is used in two different sentences in different context. So to capture that context, some this mechanism called attention came into picture. Okay, and for now, if we want to understand that how attention can understand this context, it it can understand by creating query key value vectors. Okay, now please don't confuse. uh, just give me 10 to 15 minutes, so after that you will be properly you will able to understand this attention very comfortably. Okay, so let's let's again take an example. Cat drinks milk. Okay, we have a vector that represent each word. Okay, that represent each word. Now how do we apply attention? How do we apply attention? We can create three vectors. We can create three vectors: query, key, value. Okay, and this is q1, q2, q3. This is k1, k2, k3, and this is v1, v2, v3. Okay, we we can create these three vectors for each word. For drink word, Q1, Q11, Q12, 13, K11, 12, 13, 11, 12, 13. Okay, so 21, Q22, Q23. 21, K22, K23. V21, V22, V23. Okay, and the last one is Q31, Q32, Q33, Q3. Now K31, K32, K33. And this is V31, V32, V33. Now everyone, you all are thinking that where these q1 query key value, where these vectors came, where these vectors came. So they came by multiplying this vector to the learnable weights w11, w12, w13. So by multiplying these weights, three different weights, okay, we can also, we what we can do is we can make three pairs of these learnable weights and multiply this vector to, to these weights, so to get the q1, q2, and these weights are random. These weights are random. They will adjust when we do back propagation. I will I will cover up this. I will cover up the back propagation part in the next to next video when we discuss about the full transformer architecture. But right now, to understand the attention mechanism, I want you to just understand how these query key value vectors are made. These are made by multiplying random weights, by multiplying these random weights to this vector, then we get our query vector, key vector, and value vector for each word. For each word. Okay. So now let's understand. Let's understand the attention mechanism. The idea behind the attention mechanism. The idea behind the attention. Okay. So when we Google something, okay, when we Google something, we search a query. For example, I want to buy a phone. So I search on Google, I give Google my query that I want to buy a phone. After that, it will give me, some results. Okay, and in those results, I will look for something that I want. So the results are my keys. The results are my keys, and inside keys, I will get my value. Okay, there are various phones, and in various phones, I will look what I want to buy. And after clicking on the specific link that on the specific phone that I want to buy, that is my value. Okay, so the idea is so simple that attention is using. And the idea is this: we query, we get keys, and in those keys, we select any one key and get our value. Okay, so that is why we create three vectors, query key value vectors, using our initial input embeddings. Okay, okay, let's move ahead. In Transformers research paper, attention weights, we are calculating attention weights. And broadly, I want to add up one more thing. What attention is exactly doing? It is looking at each word inside the sequence and see which word is important to the word, to that word. For example, we were discussing uh, the first sentence. We were discussing about the example. So in this, example, okay, what we are doing using attention, we are focusing on each and every word, that which word is important, that apple is referring to what, phone, I, what, okay, M is referring to I or apple. So attention is basically looking at each word, that which word is more important to the current word that it is looking. So basically, uh, it picks M. Okay, M is query. It looks at I. These are my keys. Okay, and finally the value is I, because M is referring to I. Okay, so this is what happening inside the attention mechanism, and to compute the attention scores. Okay, so in every phase we will get same number of vectors. We will get same number of vectors as we have in our input. Okay, so as you saw our input embeddings, we are taking example cat drink milk. Okay, so we have three vectors. After, so I said that for each vector, there will be the same number of vectors that have the information about the position of each word. So there are three words also. So after adding up positional encoding vectors to our input embeddings, we have now information of input embeddings plus positional embeddings. Then these three vectors goes into the attention part, and output of attention is also a set of three vectors that is same as our length of words. Okay, now in attention, how do we compute attention? So attention output will be query key transpose under root dk, and we apply softmax function and then multiply by v. This is the formula to compute attention. In this formula, uh, let's simplify this formula first. Okay, so for query, so this q part, let's take each part. This q part, what will be this q part? q11, q12, q13, q21, q22, q23. Okay, q31, q32, q33. We stack up all the query vectors. Similarly, we stack up all the key vectors k11, k12, k13, k21, k22, k23, k31, k32, k33. Okay, so q and k we understood. Similarly, we can stack up the v part values. So v11, v12, v13, v21, v22, v23, v31, v32, v33. This is our value matrix. We stack up all the matrix, all the query key value matrix to make a 3 into 3 matrices, so that it is easily to understand for all of us. Okay, now I write query key transpose. So what it means, I'm just so we all know about matrix multiplication. So we take query matrix, it got multiplied with k transpose. So k transpose will be k, k11, k12, k13, k21, k22, k23, k31, k32, k33. So this will be our k transpose, and we multiply this, and we will get after multiplication query multiplication k transpose. If I have to write, then I can write for you guys, so that q11 k11 plus q12 multiply by k12 q13 k13. Okay, now q21 q21 k21 plus q22 k22 plus q23 k23. Okay, I'm I'm right, I guess. Okay, so we all know, let me small k q21 multiply by k21 q22 k22 q23 k33. Then we will get the next thing q31 k2 k13 plus q32 k23 plus q33 plus k33. Okay, in similar fashion we will get no, I made a mistake, q11 q12 q13. Okay, now in the next row q21 we pick q21 k11 plus q22 k21 plus q23 k k13. I mean, this matrix multiplication we can do easily, and now my screen size is little low. What I can do is I can paste here the exact matrix multiplication. Just give me a second. Yes, this will be our final matrix that we want to get. Okay, this is our final matrix that we want to get. Yes, so we get our query key transpose multiplication. So then I want you to understand softmax. Okay, so this part is also 3 into 3 matrix. Okay, and now this thing, look at this thing. Why we are doing this thing? Because of the nature of dot product, we are dividing by under root dk. Dk is basically dimension of our vector, that is representing a word. And what is our dimension? 3. 3 is our dimension in our case. Okay, so we are dividing the whole query key transpose by root dk. Because of the nature of dot product, we are doing dot product here, that gives us, that might gives us a large number. And when we apply softmax function of that large number, then it gives us probability, sharp probabilities, sharp output. Okay. uh, let's understand what is softmax. Okay, so softmax is basically converting raw numbers into probabilities that sum up to be 1. Their sum will be 1. Okay, so the formula is softmax is basically e key power zi summation of power zi. So I is number of probabilities. Okay, so basically zi, when we apply softmax on this thing, then we are applying the softmax here. So this will be our zi, this will be our zi, and exponential exponent of zi, if zi is large number, then our softmax value will be large, it will be sharp. Okay, uh, if I have to tell that what do we mean by sharp, so sometimes the softmax value will be close to 0 or it will be close to 1, and I'm saying that the sum of all the probabilities, the sum of all the probabilities, suppose we have three numbers in our case, their sum will be 1. Okay, so when we apply softmax on this matrix, then when we sum up when we sum up all the columns, it will be 1. Okay, 1. And uh, and i'm saying and i'm saying that the output of softmax is sharp. It means that values might be closer to 0 or might be closer to 1. That is not good for that is not good to train our model. So to scale down the values of so to scale down the values of the dot product, we are dividing query key transpose by root of dk. Okay, and we also understand what is softmax function. Now the final work to get our attention weights is that we need to multiply this by value vector. Value is also a matrix that we all know. So this is our value matrix. So this is our value matrix, and we need to multiply this value matrix to this softmax part. That will give us what it will give us attention scores, and then we will finally get the three vectors again that represent what they represent. They have the information that which other word in a sentence is more useful, is more contextually related to that word. Okay, okay, so now let me tell you two three more interesting facts about self attention. Now, okay, multi-head attention. So here we got the three vectors. Now why it is self attention, why we said it is self attention, because we are getting information about which word is important inside the same sentence, inside the same sentence. That's why we said it is self attention, because every word is looking at other words, that will it be important to me or not. Okay, and inside the same sentence itself, that's why we said it self attention. Okay, so this is very powerful thing, this is very powerful thing, and this changed everything in the field of AI. Okay, now we understand that by using query key value vector, we get some information that which word is important inside the same sentence. Then now coming to what is multi-head self-attention. Multi-head self-attention. Self-attention. What is this? So see, self-attention is very powerful, but it also have one limitation. For example, look at this word. The chicken is ready to eat. Ready to eat. Okay. So look at this sentence and what you all can think about the sentence, that what it is trying to say. So in this sentence, the chicken is ready to eat. So there are two perspectives. Perspective one is that chicken is ready to eat, or someone is ready to eat chicken. So self-attention cannot cannot understand the two perspective of the same sentence. So that is why multi-head attention, multi-head self-attention is introduced, that can able to understand the multiple perspective of the same sentence. That's it, nothing else, nothing. I don't want to make this video very long unnecessarily, because this is the only thing that we need to know about multi-head self-attention. Okay, now move again. Now let's understand the next thing. What is the next thing? Add and norm. Okay. Also, there is one more thing, that is this skip connection. This skip connection, if you can see this skip connection. What is this skip connection? So this skip connection is used to stabilize the training. Since our input embeddings is passed through multiple stages, so to attain the original meaning of the word, we are using this skip connection. Also, when we do back propagation, when we complete the training in one pass, and we compute loss and we update our weights in the back propagation. So in back propagation, to avoid the problem of vanishing gradient and exploding gradient problem, we are using these skip connections. And there is also one more skip connection above. So it is just to stable the training process. Okay. Now let's understand the add and norm part. What is addition and normalization? So add is simple, add and norm. So add is simple. Output of attention is what? It is a set of three vectors, three attention vectors that have the information that which word is important. Okay, so now add means we are adding original embedding thing to these attention weights. Okay, so we add up, and then we do the next thing is layer normalization. Since every deep learning model, in every deep learning task, we have to look one important thing in to train in to train any deep learning model, that our values inside the vectors should not be large enough or should not be small enough. Okay, we need to we need something called normalization. Okay, so how do we normalize each vectors? So we are saying layer normalization. It means that every vector normalize once. We are not uh, doing batch normalization, that we are taking all the three vectors and then we normalize three vectors. No, we are doing layer normalization. It means we are picking one vector at a time. For example, 1, 3, 4, 6. Okay. So in one vector we have these three values, these four values. So to normalize means mean is equal to 0 and variance is equal to 1. Okay, so we want to do this. Okay, so how do we do this? We first compute z score. Okay, g score, that x minus mu upon sigma, and for that mu is equal to, we will add 1 plus 3 plus 4 plus 6 divided by 4. This is our mean. And for variance, how do we do this? We will do x minus mu upon, let me see my notes. Yes. So for variance, we are doing this thing. Okay, summation of. So this will 1 minus, what is our mean? 4 plus 4, 8 plus 6, 14 divided by 4, 3.5. So 1 minus 3.5 divided by 4. Okay, so this is like this. 3 minus 3.5 whole square plus 4 minus 3.5 whole square. So I hope you can do the basic math now. Plus 4 minus 3.5 whole square plus 6 minus 3.5 whole square. Yes. So this will give me variance. Okay. So standard deviation is square root of variance, and then we will get our z score. Okay. Yes. So we will write, so we can compute the score for all the vectors. After that, we will do yi is equal to gamma zi plus bi. These two are my learnable parameters that can be learned during the backpropagation, and the is nothing y vector is nothing but our final normalized vector. When we sum up all the yi, that will give us 1. Okay, now our values are normalized, and these values are good enough to train our deep learning model. Okay, so the final thing that we are going to discuss today, that is feed forward neural network. neural network. This is very basic. I am assuming that if you all are watching this video, you must know what are our neural networks. So, in fact, I can discuss with you this thing also briefly, that neural network is nothing but a multiple layers connected. Okay, so these are multiple layers connected inside the neural network. Yes. So this is our neural network, basically multiple layer neural network, and this is our input layer, this is our hidden layer, and this is our output layer. And in each layers, this is called neuron. This is called neuron. So we pass our vector. Suppose we have vector of three size, vector of three dimension. So v1, v2, v3 we pass, and in each neuron there is an operation happening, that v1 multiplied by w1 plus bias. Okay, so these w1 and b1 are our learnable parameters, and whenever I'm saying learnable parameters, that means that during backpropagation, these learnable parameters will change, so that when we provide input, it will generate good output. Okay, learnable parameters, parameters. Also, one more thing that we can look on, we are doing this operation, but we are applying activation function here. Activation function. And what is activation function? Activation function introduces non-linearity, non-linearity, linearity into our neural network. And these neural networks are uh, without activation function, these neural networks are nothing but just a linear multiplication of vectors. Okay, so activation functions are really important to train a deep learning mode. Okay, so this is what happening inside the feed forward neural network. Okay, so now I guess we covered all the component inside the encoder block. To recap everything let's recap everything in a shortly, that we have a input of words. First we create unique IDs of the input words. After that we assign a random vector to each word. Then we add positional information by adding positional vectors. After that we will pass our vector position aware vector into the multi-head attention. And then we use skip connection to add and normalize our vectors using layer normalization. After that we pass the input to the feed forward neural network, and the output of feed forward neural network will also be set of three vectors, and then we again using skip connection to add and normalize our vectors, and that will give us the final representation vector that have context of each and every words. Okay, so here we will get context aware embeddings that have information of other words also, that which word is important to the current word. Okay, so this is all for today's video. In the next video, we will discuss the decoder part, and I hope you like the video. If you learn something new today, then do hit the like button, and don't forget to subscribe my YouTube channel. And we are going to we will learn something new. We will learn more and more things about AI. We will do many more things. So stay tuned and don't forget to hit the subscribe button and turn on the notification so that you will not miss my new upcoming videos. Thank you so much for watching my video.